All right, good afternoon, everybody. Just a couple quick reminders. First, the coding challenge 1 is due tonight. There are pretty much straight office hours from 2 o'clock through 7 o'clock tonight. That's all available. You're gonna either do Zoom or in person. I personally hold office hours on Zoom only tonight from 5 to 6. So for those of you who need some last minute assistance, you're welcome to take care of that then. The other thing, I wanted to show you a slide that I actually am developing for next year's version, but I want to show it to you because I came up with this after talking to a couple of students in office hours, kind of reiterate void pointers and casting pointers. So the common question is like, can you help me the difference between a void pointer and a regular pointer? And what I want to do is I kind of want to cut this idea of regular pointer out of your vocabulary. And what I want you to think of is void pointers and casting kind of as a yin and yang within a computing system. A void pointer contains information that has an address and possibly an allocated memory. So knowing where it is and how much memory you have allocated, that's the structure aspect. And then when you cast it to an int star or char star, you are telling the operating system to interpret that structure of zeros and ones in a specific way that allows us to interpret it as data. So think of void star as the structure and casting as the data, and that's how you form data structures. And so I've updated the slide, so that's now on lecture 2, if you want to go back and read that as well. Okay, so first thing I'd like you to do is I'd like to take a couple minutes and do problem 1. It's identifying class methods that should be cast as const. And as always, I'm monitoring the Slack, so that way, if you have any questions or wish to discuss these problems, please feel free to do so. Okay, so who would like to share with me which methods they believe should be const? Yes. Okay, so first we have A is a default constructor. So because it's constructing information on the heap, we should not be, oh, I'm sorry, this, I just want to make, okay. So it's a default constructor, so we're constructing information on the heap, therefore it should not be labeled as const, right? So it's a good guess though. So what were the other ones you said? C and E, okay. So C is a get method. A get method, we're just getting the piece of information, so you are correct. Get coordinate is in fact one that we should call const. So another one, get Y, that's another one. So this other one, G, is one that we are going to go over in a lot of detail today. G is the other correct answer, and that is known as an operator. So that's the last one. So C, E, and G are the 3 that we should label as const. And we're also going to go over this one in H, friend operators today. And we're going to see that that one should not be labeled as const. Does anybody have any questions about choices A through F as to why or why not they're const? Okay, so let's start digging in to this idea of operators. So when I have an integer or a float or a double and I want to add or I want to subtract them, I just use minus, plus, multiplier, divide, mod. You know, for those of you who are working on the lucky portion of Coding Challenge 1, you use mod to get a remainder. You can just use these operators, and the C++ compiler, the GCC or G++, which one you're using, intuitively knows that those primitive data types should be operated on that way. However, let's say I have a class money, and I have some sort of class that has dollars and cents, and I want to make sure that I want to have a very accurate, and I say the difference between precision and accuracy. So in a float and a double, we say they are precise, meaning they are very close to exact, but they're slight differences. We can represent them with a reasonable level of precision. But with money, you don't want to be just precise, right? You need to be accurate. So we might create a class money that has dollars and cents and doesn't lose a cent here or there based on our precision. So I want to create a class. However, let's say I want to add some money. Somebody makes a deposit. How could I add that in there? If I don't define how two class objects should be added together, it won't add it. So what we have to do is, if we're doing operators such as plus, minus, multiply, or where we see a lot today, greater than, less than, equal to, and then this printing out to the screen, it will have no idea. It'll go, I don't know what to do. And that's one of the things with C++ and objects is the challenge is you have to define every little thing. Otherwise, the compiler will blow up and show you these big compiler errors. However, if you do it and define those interactions, you can really simulate real world operations. And so the thing that I've been talking about, this overloaded operator, we can, in the .h file, define the operator declaration. I declare that I can do this, and in the definition, we go into details. So the way it works is that the return type, I can either do, if I'm doing A equals B plus C, then it's going to return, for example, a money object. So if I have money C equals A plus B, where A and B are also money objects, the return type would be money. If I have A is greater than B, so we're trying to see who has more money, the return type will be a bool, because we want to compare whether it's true or false. The next thing you need to include is the keyword operator. We are performing an operation on multiple elements. We're comparing them, we're adding them, we're subtracting them. The next thing you need to include is this thing that I have here, unary type. And that is plus, minus, greater than or equals to, output, input. So if I want to do an operator to add values, I would actually say operator plus. Does that make sense? Yes, question. Operator plus, you actually have to, I'll show you code examples, but you have to have the keyword operator and then the unary type. Both of them must be there in C++. Did that address your question? I'll monitor the Slack as well. So that's in the .h file. And my slide is wrong, my apologies, that should say .h. In .cpp, we do the same thing, except you have that class name : before it. And then inside the .cpp file, I would have this. So one crucial detail that I want to point out, I'm going to emphasize this over and over again, is why is it that I'm doing these operators and I insist that that should be called const? So that was choice G. Why am I saying that choice G is going to be const? What I'm going to show you in the next couple of slides is what values are actually calling, what objects are actually calling the operator, and what objects are being returned and which objects are being called in. If you understand that, it makes it much easier for you to be able to code these operators. All right, so for example, let's say I have a complex complex plane, and I have A, B, and C, and they have floats that can represent, that they have floats that can represent the real and imaginary on those planes. And I want to be able to add them together for some reason. Here is what's actually going on. I'm going to re-emphasize this again in the next few slides. The value that is actually calling the operator is A. The value that's calling the operator is A. So what's happening is it says operator plus, and then it has const, complex, call by reference, and I'm going to say RHS for right-hand side. This one for right-hand side, that's B. So the A object is calling the operator, and it brings in B. And I'm going to return a new object, and that's C. So what does this mean? This means that I am not changing the value of A, and I am not changing the value of B at all. So therefore, if there is a constant version of object A, if complex A should not be changed for any reason, I want to be able to still perform addition with it. So therefore, that is why the method is const. I also want to be able to take in a value B that can be const as well. That shouldn't be changed. And that's why we're passing in this value. All right, so let's go into a little more detail. The object performing the operation is B, and we see that B here is in green, and is performing the operator, that's plus. C is the right-hand side. Therefore, I want to be able to say, well, B and C aren't changing in my addition. If I add 2 plus 3, 2 and 3 are not going to change. So I want those values to remain const. So B is the object calling the value, so that should be const there. And C doesn't change, and so that's why it's const. So we start in the middle, and B is the object performing the operation. B plus C. Then we go to the right, RHS is C. That's the value that is being called by reference into B. So we say that's const as well. And what this allows us to do is two different things. We're going to see this. First, if we call by reference into an operator, we will be able to call the private members of RHS. So it gives us a little bit, for performing these together, we should be able to access those. I'll show you examples in a little bit. Okay, so we have a question in the Slack. Is operator being called by A, the plus? Correct. So the question in the Slack is, the operator plus is crucial to be able to make this. You have to tell the C++ compiler that you're doing an operation and specify which operation you're doing. So they have to both be there. Did that address your question? I see another question being typed. But... All right, awesome. What does RHS stand for? All right, RHS is just simplified for right-hand side. So when I have A equals B plus C, B is the calling object, and C is just on the right-hand side. And a good reason to have that is if you're writing an operator for greater than, then A greater than B means that A is calling the operator and B is on the right-hand side. So you see that, and yes, ampersand RHS is the actual syntax. In C++, you can actually do the ampersand after complex, in between them, or ampersand RHS. All three will compile fine. What that generally means is complex, ampersand, RHS. That's the way I present it. So did that address your question? Yeah, see, there's another question. Awesome. This is great. Good job. All right, glad to see it. And then once that question's typed, I'll come back and look. All right, in the meantime, let's go to the last part. So we're going to get our Beyonce on. And we've gone over here. Now we're going to go to the left and talk about what's going on when we return this object. In the method declaration for this operator, we are going to create a new object, and we're going to return it. So we say 2 plus 3 is equal to 5. What we're saying in C++ is I have an object that represents the value 2. I have another object that represents the value 3. I want to call by reference, so that way I'm not making a copy, reduce the amount of memory that we're consuming on the stack, and I'm sorry, on the heap. And then we create a new object that returns 5. Does that make sense? Okay, so let me see if so the question is, can you show the code for function definition? I will do that in a moment. So what's happening here is this is a new object, and it's going to be returned by the method, and it'll be a new object on the heap. So first, what I would like to do is I have a class complex.h, where I have two integers, real and imaginary, and I have a overloaded constructor, I have get and set methods, and then I have several operators. And I want you to focus on these 5 for right now. Ignore those friends. We see that that follows the same pattern. I have plus, minus, I have an equals, equals, and getting back to the question from earlier, we now see that right-hand side allows me to differentiate between those two. All of them are const because I can perform all those operations without ever changing the value itself. And I'm passing const because when I'm doing a comparison or I'm doing an operator, I do not change them. Does that make sense? So now what I do is I want to show you the CPP. I want to show you the method definitions for complex. So let's go up here, and I'm going to show you what's going on with all of these. So for plus, what I'm doing is I'm creating the new object, and then I can define how I want addition to be done. So I am telling it how to add. If you're going to add two objects of this type, it must be done in this specific way. So we see that I have the return value, complex : : operator plus, complex right-hand side, and const. So then I say that the real and imaginary private members of this new complex object are equal to the sum of real plus RHS of real. And the reason we can do that is because it's an operator and we call by reference. And then once we do that, we return. All right, so Farah, did that address your question? So we see the same thing for subtraction. When I have equals, equals, what I'm able to say is, if real is equal to the right-hand side's real, and imaginary is equal to the right-hand side's imaginary, return true, otherwise return false. So this allows me to be able to compare these two types of objects. And then greater than and less than. And then we'll ignore this for now because that's a friend operator. All right, does anybody have any questions? Yes. This is C++ syntax. So right here, what's going on? Are you talking about this? I'm sorry, which one? So RHS is the variable here. And so in the class complex.h, it has two private members, a real and imaginary. So what's going on here is RHS is the variable name. And then what's going on, normally I can't access the private members, but in operators I can. So in an operator, what this allows me to do is it allows me to say, all right, RHS.real is RHS. This one is the calling object, which if we did A is greater than B, what I have here is an abstracted version of this. So that does the exact same thing. So this is C++. And C++ has a bool as a member of the standard template library. Did that address your question? Yes, the variable is defined here in the method definition, as well as in the method declaration here. As I saw there was some typing going on here. How does the compiler know which overloaded operator to use? Is it based on what the left-hand value is initialized as? It's based on what's actually called. So I'm going to now go to complextest.cpp, so this will help address your question. And I want to walk through step by step what this code is doing, and then we'll see how putting it in this way in the class has abstracted complexity for the person using the complex class. So here first, just to show the value of const, I've said C1 is a complex object that cannot be changed. It is constant. And so all these comparisons that I do should allow me to be able to make all these. So then I have a complex 2. I have a set imaginary that changes the value. Ignore this for a moment, that's a friend operator. But here are all the overloaded operators. So C1 here is the one that's actually calling its less than operator. So what that means is C2 is going to be RHS. And so C1 will have this copied, called by reference, and then return bool. And so it does the same thing here and here. And then I have addition and subtraction. So C1 is the calling object, C2 is called by reference, and C3 is the new object that we create. So because you have to do it in that specific order, that's why we have to do it that way. But since this is a lot simpler, if you know if it's already been provided for the user, they can just say plus. So did that address your question? So let me run make complex test. And it's going to hang there for a minute. I'm going to do Control Z because I haven't gotten to friend operators yet. Okay, so here's all the code that I was just showing you. So it's there available in the slides as well. So now what I like to do is to take 3 minutes and work on problems 2 and 3. Okay, so problem 2, who would like to tell me their guess? Yes. B is absolutely right. So it's asking what's the valid operator for a minus operator. So this is correct because we have to bring in the value by const, we call by reference, and it's a const method itself because we want to be able to subtract both of those values, get a new result without changing any of them. And so what about number 3? Which one of those is correct? Yes. A is absolutely right. So it's the same concept, except we return a bool because we want those to be done that way. So good job. Okay, so the next thing is a friend operator. So an operator is when we're comparing two things and create another thing, or we're comparing them and returning a bool. The crucial thing with a normal operator is that you are calling only objects of the type that's calling. So we do money A equals B plus C, where B and C are money. The calling object is a money object, and C, which it's calling by reference, is also a money object. But that's not always going to be the case. And in most often, that is going to occur when we need to read out and read in. So we're using standard C in, standard C out. You've done the labs, and most of you have completed CCO1, so you're familiar with the input and output streams. So if you want to do things like that, you need the piece of information, but you also need which stream you're writing to. Is it a file stream? Are we printing to the terminal? So we need both of those pieces of information, and they're not both of the object. So if it was money, we need money and the stream. If it was complex, we need a complex in the stream. So when you have a different object than the one you're bringing in, you have to label it as a friend operator. So we see that here we have O stream called by reference, const complex called by reference as well. And here for input, I have standard I stream in complex C. And I'm going to go into more detail in a moment about why we return O stream and I stream. But to give you a preview, this is going to go all the way back to lecture 1, where I showed you that the hello world actually had 2 underlying pointers underneath it. And so now how do we communicate what's pointing to the output? Okay, so here, what we're going to do, and so this will get the question, explain why we need const. Okay, so I will explain this in a moment. So think of a friend like this. So friend, if it's just objects, you do operator. If you need to bring in a different type of object, you're bringing in a friend. Think of it as a +1. And so I might be dating myself a little bit by sharing a Mitch Hedberg joke in class. Does anybody know who Mitch Hedberg is? Please, someone raise your hand. No. Okay, so Mitch Hedberg was a very popular comedian around the early 2000s, unfortunately passed away. And he told a joke that I use that helps convey the idea of friend operators versus normal operators. So he's like, it would be cool if you could eat a good food with a bad food, and the good food would just cover for the bad food when it got to your stomach. Like, you could eat a carrot with an onion ring, and they'd travel down, and they get there, the carrot say, that's cool, he's with me. Oh my gosh, none of you laughed at that joke. Okay, so it's not just me. Mitch Hedberg doesn't get laughs either here. All right, so the crucial thing is the carrot is the complex, and the onion is the output stream. And that's why he's their friends. They come in together. Okay, so passing const to friend function. So this is going to be addressing a question that was just asked in the Slack. So when I'm reading out, I am not changing the value to const. I'm not changing the value at all. So you want to pass the OF stream as a const variable. And when we call by reference, we can access the private members. So to show you, let me go back to the code real quick. In the complex.cpp file, when I have this output operator, what you're going to see is I have the standard O stream output, and then I output c.real. And when I do it as const, I don't want to change complex. So I'm saying I want to be able to have const objects that are passed here and can be printed out. If it's not const, that's okay, but if it is, we allow it to happen. And so here, what I'm doing, I'm saying if it's imaginary is less than 0, then I can say -I or +I. So that way I can just indicate more simply to the user, it should be real minus value imaginary. So here we're conveying these values. You can actually use these operators to convey properly how you want the output to look. Okay, why do we need complex operator for 2 but not 3? I'm not entirely sure what you mean exactly by that, but here, oh, you're asking about the, I haven't gotten to that specific point. I understand what you're asking now. Okay, so what's going on here? And so let me go over to address that question by saying, how do we define them in the .h for this versus the .cpp? So in the .h method, you put friend, standard O stream that you return with a call by reference. And since you've now worked through streams.cpp, you have a little familiarity that streams are basically file pointers that you learned in C, right? So by calling it by reference, you're keeping track of where you were in the file stream or where you were on the terminal. So that's why we have to call by reference, but also we have to return. And the reason why we have to return for iStream and stream is if we have standard cout and I say ABC, and then I say 3, 4, 5, it's going to, this is going to be passed to it. I'm going to pass a complex value, but then I have to return because it's going to continue to propagate along the line. So if I want to read in multiple values, I use iStream or OStream. I want to be able to print out multiple values in the same line of code, which is why we simultaneously have to call by reference and that we have to return with a call by reference as well. So both of these are required for both OStream and iStream. Does that make sense? Okay, awesome. And then to address the question so the first question is, because I'm reading in and I want it changed, it's not const, whereas here it is const, because we don't want it to change when we're reading out. The other thing is, in the .cpp file, because it's a friend operator, because it's a friend operator, do not put the class name in front of it. So here I have an example of the OStream, and this should address the question about complex operator. Because it's a friend, we don't put the name there. Furthermore, in the .cpp file, don't put the keyword friend. So in .h, friend, make sure you're returning standard OStream call by reference. Then you call by reference in the call, as well as calling by reference of an object. And because you're bringing in a caret and an onion ring, when you get here, you don't use the keyword friend, and you don't have the class name in front of it. So that's C++ syntax, and that was a decision made by the C++ inventors. All right, so those are the two most recent questions in the Slack, so please let me know if that addressed your question. All right, so if there are no other questions, I'm going to continue. So here is the input stream where I can read in a non-const version, and I can read in using the input stream, and then I return. So I can create temporary integers, read into them, just like you did in the input stream in your assignment, and then you can call the set methods to update those values, and then return the input. And so now let me make complex tests and let it finish. So what I've done is all of these, I have printed out the outputs for the values for that specific complex. So now I can say 3 and 27, and it'll print out 3 plus I 27. So now I'm using the input stream, using the operator that we designed to be able to read in that information. So we have a question. Which one is the call by reference and which one is return by reference? So that is going back here into dots. So it's the same in .h and .cpp. So let me scroll down here. Here, this standard O stream is the input. So if I have standard C out and then some sort of class object, the class object they are both passed in. The operator here is taking standard C out and complex object and performing the operation. But then since I might have something else here to print out later, that is why I have to return with the call by reference. Did that address the question? Why is the OStream method not const? The reason why the OStream is not const is because we're constantly changing it. Whenever we're printing something out, it's like a file pointer. You print something out, it moves down. So it actually has to be, it cannot be const. Because remember, we allocated hello world on the stack in the first day of class, and the OStream goes, all right, here's H, I move 8 bits down, here's E, so it has to be able to move. So therefore, it cannot be const. Did that address your question? All right, awesome. Okay, so quick thing, if you try to call an operator that you haven't defined, and I want to give this as new C++ programmers, this is a common mistake. You think you've written the appropriate operator, you called the operator, you wrote plus, you forgot to write minus, and you have minus the objects all over the place. When that happens, you might get one of these huge compiler errors that look big and scary. And you're new, you're freaking out. What the heck happened? Why is this happening? I thought I had the program done. I'm never going to pass data structures. I'm going to go home and cry. Fret not. The way to address this is to always scroll to the very top and look at the first compiler error. And here, what it's talking about, it says no matching operator. And what this is saying is I'm here trying to print out C1, and whoops, oh, I forgot to write my friend operator for output. The reason why it's so big is because since C++ is object-oriented, it's now trying to go through the standard template library and look for every possible version of the method that could possibly match what you were trying to do. And so all those things in blue, those aren't errors, those are just, okay, I didn't find it, I tried this and it didn't work. I tried this and it didn't work. I tried this and it didn't work. And it just goes on, but if you're new, it can look really scary. So always go to the top, look at the very first one in red, take care of that, and then it'll knock off a big chunk, if not all of them. Does that make sense? So that should help you when you're working on future assignments. Do we have to overload operators for specific classes? If you want to be able to do a specific operation on a class, yes, you must. Otherwise, you'll get this big error. Because when it's an object, it doesn't know how to do it. You have to then say, all right, here is the operator. Here's how I've defined it based on the private members that I've encapsulated. Did I address your question? Awesome. All right, so I see there's another question typing up. So let me move on to the next slide while we're waiting. All right, so yeah, I showed you, go to the top and you can address that, and that makes life a lot easier for you. All right, so up to this point, every class that we have done has fixed private members that we've encapsulated. When I say fixed, it means it is always an integer, it's always a double, it's always a float. But what happens when I want to perform the same task regardless of the type that I'm getting in? So for example, I have a common meme, and the idea is that somebody's passing something to him and he looks at it and he's angry because there's something on the note made him mad. And you can fill that in with whatever you like, right? The joke is it's the same beats on the joke, and it's the same result. So for example, this is one that I actually saw. So someone's code, they put it on Stack Overflow. Stack Overflow, you grab it off Stack Overflow, you then put that code into your code, you then put the code into the integrated development environment. The IDE does linting. The linting makes tokens, so that's a compiler thing. So for those of you who take compilers, you'll learn all about that. The parser, then it goes into the preprocessor. The preprocessor then goes to the compiler goes to the assembler goes to the linker, which you're familiar with for those of you who tried to figure out linker errors such as the no tabs. Then it goes to the operating system. The operating system takes the result back to you, and then you're mad because that code has a seg fault in it. I say the internet has code that is dark and full of errors. So how can we take advantage of this idea of templates that does the same process, but we want to be able to do it on different types? So a template is how we can reduce the complexity of having to do all this function overloading. So first we said, all right, in C++, we might want to do the same thing with an overloaded function. And instead, we can simplify it even further by saying, all right, I am going to pass the type as its own input itself, and then have the compiler make its own version of the code that we put onto the instruction stack based on that template. And so the first thing I'm going to show you is a function template. And in C++, we have a template parameter that I'll show you in a moment. And in order to do that, in order to write the function, we have to have some placeholder that says whatever the type is going to be, we're going to put that in there. And that is known as a generic parameter. And generic parameters are very important when you're constructing data structures, because the generic parameter says, I can do this generic parameter, I can do use this data structure to do all different kinds, of operations, regardless of the data type. I've seen several data structures where it works perfectly good with int. I'm like, all right, template it to a double, and then it falls apart because they're using the same type to point to locations as they were to store data. So that's why I'm emphasizing void pointer and cast pointer, because the idea of data structures, to be really good at it, you have to understand the difference between data and structure. So it's the same kind of idea with templates. I want to be able to structure it regardless of the normal type. So we're going to call this a generic type. And so here is an example called print function. The way it works is you say template, that's the keyword, and then you have a less than and greater than sign. And then the generic parameter is class T. So T is a variable that is a generic type. So then I say print func, and you can see that here I have uppercase T, var. And then I call standard cout, print the value, and return it. When you were taking C, when you took Fun Comp or Introduction to Computing, we had these parameters that we had to pass, these output parameters that indicated the specific type. So therefore, we couldn't template. Here, what this allows us to do is say, okay, if I want to print out an integer, I can do that just as long as I'm passing an integer to the function. If I want to do it as standard string, if I want to do it as a float, I want to do it as a double, and I will let the object-oriented C++ do the work for me. And so here's what happens. If I want to say, I want to have a generic type, I put a template class identifier, and then I have the function declaration uses that identifier to substitute the type when it's called. So here's an example. On the left, I have that template. And so you can either do it on, like I had on the previous slide where it's down here, or you can have them on the same line. Both of them will work fine. And so first I have an integer, I have a double, and then I have a string. And then this function is called printfunc. And I say printfunc I, printfunc j, and printfunc k. So here is what the computer is doing when it sees my code. What it's going to do is it's going to say, all right, I call printfunc I, and I have an integer I. So I'm going to create a version of this code that has an integer passed to it. And it performs the print, and it works. Then I call the templated function. It's passing a double to it. So now it's going to put a copy on the instruction stack where it passes a double and interprets it that way as a double. And then the third time it passed the standard string, and it does the exact same thing. So what the template means is, all right, I have a template. It's just like a meme. We want to get the same reaction every single time, except whatever somebody puts in there, we can use it to interpret, so it's a very specific joke, right? So we had that generic, they passing the note, but then I went through this long-winded thing, but it had the same thing at the end, where the person was mad and they didn't like the note. And we see that it will print out those exact values. So what that means is we don't have to write several copies of printfunc. That's the benefit of having templates and being able to use generics. Does that make sense so far? Right. So now let me go back over. We remember this definition for data structure, and now let's dig a little further using this new kind of computational thinking of templates. So a data structure is a method for collection and storage of logical data values in a computing device. The second part is and associated approaches for performing operations on those values and collections. And the third part is that progresses efficiently through the machine. So now we're kind of getting this idea of how do we collect data? We learned the fundamental of it with a void pointer. We're casting the char star. We collect and store data. We've now structured it in the way we want. And up to this point, we've only structured it when we know the type that we're casting to. So we have char star, int star. But now we can make it a generic when we allocate memory. And this is one of the reasons why it's important to understand what a void pointer is. Because a void pointer points to some amount of memory, and then we can have our structure that amount of memory based on the type we give it through the generic type in the template. And that is one of the major fundamentals of data structures. So, okay, so that's basically what I've said. All right, so first thing I want to do is I want to go again, lowest level, procedural. We have this piece of code here, temp void node, and it's the same thing that we did earlier this semester. And before I passed doubles, floats, ints, and then we performed some sort of operation when we knew the amount of bytes to add to get to a specific location. But now what happens if I just want to create a node and I want to have 3 different values and have a variety of different values based on what it is that I want the program to be able to do. So here we have the same set node values, except this time I have 3 generic inputs. Class T, comma, class U, comma, class V. You have to say the class name before it every single time. So now what I'm doing is I still have that void pointer. Now I have T, U, and V. And now the casting part means I can point to the location, I can cast to it, And because I've defined the class, I know at the beginning what the size will be of that specific type. And then I move, and then I do the same thing again with U, and then I move, and I do the same thing with V. And now I can do the same thing with printing. So what this allows me to do, and I'll show an animation of this in a little bit, is I can create a node with 3 private members and perform that pointer arithmetic in an efficient way, efficiently progresses through the machine before I even know what the type is. So that is one of the reasons why really understanding what's going on underneath the hood allows you to be able to build really strong data structures. So here, what I say is, all right, I'm going to make a double float and int, and then I allocate the memory to void size. So now I'm giving it structure. I know where it is, and I know how much information I have. Then I would pass the information, then print the values, and then I free the memory. But I have an issue here, and this is where I want to reinforce something that I mentioned in lecture 2. So when I run this compilation, we expect it to print out negative 0.625, 1.5625, 131. So let me run make temp void node. And first, I have these errors. So what should be happening here is all of this ensures that we are trying to keep everything secure. So it'd have to be reference, and then I would do T star. Sorry, this should be equals, my apologies. This should be T star reference plus size of T. So now we're being very careful about how we're doing everything with structure. So I'm going to copy this and just do that for you here, and then do the same thing in print node values. And so that's what those errors are about, because we want to make sure that we are very strict with how we're doing things. But I'm going to show you that even this is not perfect. We see that we've cleaned everything up, but now our values look very wrong. See that? I want to show you why it is, and this is one of the reasons why I use that W conversion flag. What's going on in the code is that the C++ compiler, okay, there we go, now we're zooming in. The C++ compilers I've mentioned before assumes decimal to be a double. Those are 64 bits, right? A float is 32 bits. So now I want to show you what's actually being done here and why it is that you can want to cast to float. So there's everything there. There's all the fixes I made. And now we see that it's double float and int. So what I've done here is I have, because I'm passing a void pointer, I can pass these as a template to indicate what the generic type should be in that specific order. The reason I don't have to do it in set node values is because these have a type. And so that fills the generic types in. But here's an issue with that approach. I see there's a question in the chat I'm going to show you in a moment. Actually, I think I just addressed that. So because we're only passing void pointers, if we don't have inputs that interpret what's going on with a generic type, like for example, here we have the inputs TU and V, and they can map to the template. If we don't have that, like we do here in print node values, we then do this template. Did that address your question? Awesome. Okay, so here's what's actually going on, and here's why the code goes so bad. So I said it makes decimals by default, and then we do the addition. So when it passes a double by default, it's actually creating a 64-bit value, not a 32-bit value. And then when I tried doing it with print node values, I actually get the, oh, sorry, where's the, I have this in the wrong order. So let me show you what's actually, I thought I had it right there. Oh, yes, there it is. Okay, sorry. I put it in the wrong place in my slide. So what I would like you to do is work on 4 and 5, and just know that problem 5 has an incorrect result for the value that's going to print out. And I'm going to go over in detail why it prints the wrong value out. Okay, so who would like to tell me what they got for problem 4? Yes. C is correct. So what's going on there is just what I described, and what's going on with the float. I'm going to go into the animation that describes this in more detail about what happened with double and float there. And who would like to tell me their answer for number 5? Anyone? Bueller? Yes. A is absolutely right. So it prints out the correct values. So let me go over what's going on here about float and double. So why did temp void node run badly? So here in the chat, I think we had, okay, so both of you got the answer right, very good. So what's going on is that when I create this, I create the node size of a pointer, long unsigned int. This would be 64 plus 32, so it'd be 96. And then I create the void pointer that gives me the structure, the amount of bits and the location. And then I call set node values. When I just have them like that, it signs it by default as a double. So I have 96 bits allocated. But what's actually going on is I have the void star reference. And when I pass it, I'm actually making a copy. So I'm going to tell you something in a little bit. It's actually passed by value. So what's going on is I allocate this as a double. So that's 1.5625. That's why that's correct. Then I perform the addition with the change that I made to the code. And then when I pass it that way, it thinks it's a double, even though I've only allocated 32 bits. So what happens is I allocate 64 there. I've gone over the amount of memory. And so to give you a preview of what's going on, this is a computer architecture preview. So there's a command lscpu. And when you type it, it gives you all the information that you need about what's going on with your computer. So here, this Notre Dame machine is actually a quad-core AMD Opteron processor 2356. It has 32 and 64-bit modes. We select the 64-bit mode with the -M64 flag. And then it has this little thing here that says little endian. So the term endian actually originates from the book Gulliver's Travels, where Gulliver goes to a location where they're in the middle of a war, and they're fighting over which end of the egg to crack. Should it be the small end or the big end, little end or big end? So that kind of has that origin. And big endian is how we would normally read, from left to right. But there are ways, and you'll learn about this in computer architecture, where it benefits you to read from right to left, or little endian. And the computers that we're using are little endian. So what's going on here is that normally 1.5625, that first line has 2 zeros, a few ones, and intermission. That's a little outside. That's for logic design. You'll learn precisely how to do that. But when we do little endian, it flips. So now the first 32 bits are 0. And so that's a 0 for a single precision for a float. So what ends up happening is I allocate in those 64 bits, first all zeros, and then I have a combination of zeros and ones. But then when I call double and float to print it, what happens is, okay, I pass T and U with the generic types. I get the first 64 as I anticipate. I add 64 like we did before, but then I only get the first 32. So that's why it printed out 0, because of improper data structuring. So when we do that, we can no longer guarantee the effectiveness and the reliability of the data. Does that make sense? Okay, so there's all the stuff that I've said about void star, except for one thing. When I pass by value, the previous value is retained in main, right? So with a void star, I'm actually passing a copy of the pointer location. So when we go back out of main, where it was pointing to before is preserved. But what if I want to change it? And that's something I'm going to have to do with trees and graphs to be able to point to a different location to a different node when we do reordering. Does anybody have any ideas? If I want to change the value and have that value preserved without doing anything, what do you think I would need to do? I'll give you a hint. It was in the CC1 reading. What did we do when I wanted to change a value but not have it be over complex? So it's the C++ simplified version. What is that called? Yes. Call by reference. Absolutely right. So we're actually going to call a void pointer by reference. So look at this. Void star ampersand means I am going to call the void pointer by reference, and it will actually change the location that I'm pointing to. So that way when I go into main, it's preserved. Does that make sense? So that's actually, before it was passed by value, now we are actually calling a pointer by reference. And so here, what I've done in void node call by is I just have an update. So I make it go down and it's updated with the double node and minus size of double. So I cast it to preserve security, and then I go back up the stack by subtracting double, because when I called it by reference, the changes were preserved. Okay, so see, we now here I've cast it to float. That's the exact same thing. So that error that I showed you It was the Ariane 5 rocket. So that was the exact error. It was templated. It did it incorrectly. $1 billion rocket blew up. So we print the new location, resets to old. I'm going to skip past this a little bit, but that's the general idea. So now we're kind of taking this idea from templated functions to templated classes. We can actually template a class. So now this allows us to be able to move to this object-oriented programming where we can focus on structure and then allow the templates to apply the data for us. So I first have a templated class here in A1_H. And what happens is, before the class definition, I have two private members, T and U. And I'm going to have the generic types here, class T and class U. And when I create that templated class, it will fill that all in for me. And so I have that same kind of default constructor where I'm printing out the address and the value, just like we did before when we were going over imperative programming. I have the overloaded constructor, and the templates allow me to be able to do all of this. In the .cpp file, when I actually create the objects, so just to review, if you just add it like that, you can add them in before. And then when I create a templated class, I just have that same thing where I put in double double, and then I have another class that is care, and here I have another one of int care. I have double and float, so I have a variety of different types, and underneath the hood, it's doing all that work for me. Does that make sense so far? A crucial aspect of templates is that, so we've got all this, which I've shown you, is that we don't know what the type will be until we actually run the code. Does that make sense? As a result, remember I told you I was going to sound like a hypocrite when I told you you always had to separate .cpp and .h files? When you do templated classes, you must put everything into the .h file. Then the reason why is you don't know the types until runtime. And so I have an example here, and I have a bad.h where I'm trying to separate everything out, right? And I have my templates, I have my method declarations, and everything looks good here. And then in .cpp, what I'm doing is I'm trying to put in all the templates for every method. But the issue is because I don't know it until runtime, it can't fill those all in, and I get a series of compiler errors. So if I run make template bad, what will happen? Okay, so here's everything I just showed you. And then if I try to compile it, I'll just get all these undefined references. And the reason why it says undefined reference is it goes, hey, wait a minute, I don't know what your type it is. I don't know how to properly allocate the data on the heap. So this undefined reference is saying, I don't know how to structure your data. It doesn't make sense to me. So that's why you have to do everything in the .h file. Okay, so you can see with the constructor, I have everything that I would need there. And what I want to do next is talk to you about this thing called the rule of three. So this is where we're kind of going to conclude lecture today. The idea behind the rule of three is that if I allocate memory on the data heap, I need to eventually be able to deallocate it. We need to free all that memory before we actually begin the program. Okay. So what's going to happen is I now need to say, I'm going to have something called a destructor, which by default is going to free the memory. So that destructor right there, I don't have anything inside of it. And the reason why is because my templated class doesn't have any pointers. And we're going to do a lot of that later in the course. But for now, we just have a destructor. and it's implicitly called when we run when the class is called at the end. And so it frees the memory, and we're going to call that a delete operator. Does anybody have, let's see, okay, no questions? So here it is, zoomed in a little more, deletes anything. So if you have a pointer that you allocate as a private member, call the delete operator, and we're going to see several examples of that next week. And that is the equivalent to delete this. So it frees the memory and then frees up the register. The other thing with this rule of 3 is that there are 2 other methods that I have to write. If you write one of them, you have to write the other 2. And the reason why you have to write the other 2 is to ensure that you have properly allocated and deallocated memory. And these other 2 are a copy constructor and an assignment operator. A copy constructor is if I say A equals B, right? I can actually call a previous object and make a copy. The other one, the assignment operator is A equals B. And if I have A and say other A, right? I can pass that, and that's known as a copy constructor. Hey, does this make sense so far? Okay, let me take. Okay, so let me go, I'll get through the destructor and then I'll ask you to do the last 2 problems to finish lecture. So a quick note on the copy constructor. I'm going to share with you this, and then we'll go over the last 2 problems. The this operator here, if I say A equals B, then the calling operator is A. And this assign, const TU ampersand assign is B. What's going on here with this does not equal assign is if I can save effort by just saying, if the pointers are pointing at the same location, then that means they're the same object. So let's make sure that we're not doing redundant, unnecessary work. If I say A equals A, it just goes, cool, A is A. We leave it alone. But if I want to assign something, I can go through the private members and print them out. I mean, and assign them from the assign to the this operator. Does that make sense? I'll be going back over this at the beginning of Tuesday's lecture. But what I want to do is I want to kind of go over the last 2 problems with you in the interest of time, because we only have a minute left. Okay, go away. So the last 2 problems, 6 and 7. When are the templates usually instantiated? So they are instantiated at compile time. So it's B. Because that's why we have to put everything into the .h file. The last thing, and I'll go over this in more detail with an animation, it says, what is the expected result of the output? So I want to walk through it with you, and we can see why it is that it gives us the answer that we're going to get. So I create 2 objects of A that are templated, int and double. And so I pass 3 and 2, 3.3 and 1.1. And then I say cout get div. So what's going to happen is, first, I create int, and it's going to print out A and B. So it's going to print out constructed 3, 2, and then it's going to create the double, and it's going to say constructed 3.1, 1.1. Then I print out the result of get div. So t get div, when it's an integer, and it's templated that way, 3 divided by 2 will give 1. And then with double for A2, it'll give 3, because 3.3 divided by 1.1. Now what's going on here, and this is what I have with the animation that I'll show at the beginning of Tuesday's lecture, is it calls the destructors, but it calls them in the opposite order that you constructed them because it's going up the heap. So it's going to call the destructor for A2, and then it's going to call the destructor for A1. So it says destroyed A and B. So it's going to say destroyed 3.3 and then 1.1. And then it's going to say destroyed 3 and 2 because it's going to delete A second. And so that choice, we see that it says, I believe it's B is the correct answer. It is. So that's the correct choice because it's going to put it onto the stack in the heap and then take it off in the opposite order. Does that make sense? All right, so I fixed a setting on the assignment. You should now be able to have the unlimited submissions for the lecture assignment. And that update's been fixed, so you can make that change. And if no one has any other questions, then you are dismissed, and I will see you on Tuesday. Unless you come to my evening office hours tonight, then I'll see you there in the Zoom.